In the last episodes, we learned a hard truth about the sea. Light dies fast, but sound survives. And we learned a second truth that matters even more for submarines. Speed can betray you, because cavitation turns water into noise. So the submarine's real battlefield is not the surface. It's not even the map. It's the physics of water, layers you can't see, but that decide what you can hear, and what can hear you. Today's question is simple. If the ocean carries sound so well, why isn't everything detected all the time? Why do ships and submarines sometimes seem invisible, even to sonar? The answer is, the ocean is not one uniform medium. It's a stacked system of layers, and sound bends through those layers. And that bending can create something that feels almost unreal, a corridor where sound travels ridiculously far, and nearby zones where sound simply doesn't arrive. This episode is about that invisible geometry: thermoclines, refraction, shadow zones, and the deep sound channel, not as mythology, as a measurable system with numbers. The model card. What problem are we analyzing? We're analyzing one mechanism: how changes in temperature and pressure reshape sound paths so that detection range can expand or collapse without any new technology. This explains three real-world effects. 1. Why submarines care about depth like pilots care about altitude. 2. Why the same sonar can work one day and fail the next. 3. Why low-frequency sound can travel across huge distances while high-frequency sound dies quickly. If you understand this, you stop thinking of sonar as a magic sensor. You start thinking of it as geometry inside a moving fluid. 3 terms you must know, simple, visual, with example. Term 1. Thermocline. A thermocline is a layer where temperature drops quickly as you go deeper. Because sound speed depends on temperature, a thermocline creates a sharp change in how sound travels. Example. A submarine above the thermocline may sound loud, while the same submarine just below it can be harder to hear. Term 2. Refraction. Refraction is the bending of a wave as it travels through layers where its speed changes. We know it from light in a glass of water, but sound does the same thing in the ocean. Example. A sonar ping can curve downward and miss a target that is actually close by. Term 3. Beamforming. Beamforming is how a sonar array combines many hydrophones to listen in a preferred direction, boosting signal and suppressing noise. It doesn't create sound, it shapes listening. Example. With beamforming, an array can detect a faint, low-frequency hum that a single sensor would lose in the background. Keep these 3 terms in your head. Now we can read the ocean like a layered machine. The data triad. 3 sets of numbers that matter. Data point A. Sound speed in seawater is fast and sensitive. Typical sound speed in seawater is around approximately 1,450 meters per second. That's over 4 times faster than sound in air. But the key is sensitivity. Temperature changes can shift sound speed by about 4 to 5 meters per second per 1 degree Celsius near the surface range. That doesn't sound like much, until you realize tiny speed changes across depth create curved sound paths over kilometers. Data point B. Loss grows brutally with distance. In open water, a spreading wave loses intensity as it expands. A classic rule of thumb: in spherical spreading, transmission loss rises by about 6 decibels every time distance doubles. So even without absorption, distance alone can erase a signal. Data point C. Frequency decides how far sound survives. Water absorbs high frequencies much more than low frequencies. Typical ballpark numbers. Around approximately 0.04 decibels per kilometer at 1 kilohertz, and around approximately 1 decibel per kilometer at 10 kilohertz. That difference is enormous. It's why low-frequency sound can travel far, and why high-frequency sonar is sharper but shorter range. Now we combine these 3 data points into one picture. Speed changes with depth. Spreading each signal with distance. Frequency determines how quickly absorption kills you. This is the physics behind hiding and hunting. What actually happens? The ocean bends sound. Let's build intuition with a simple mental model. Imagine the ocean as a three-layer system. 1. The surface layer, warm, mixed by wind. 2. The thermocline, temperature drops rapidly. 3. The deep layer, cold and stable, but pressure keeps rising. Temperature tends to decrease with depth, especially across the thermocline. Pressure tends to increase with depth, and both affect sound speed. Near the surface, temperature dominates. In the deep ocean, pressure dominates. So the sound speed profile often does something weird. It decreases from the warm surface down into cooler water, then increases again as pressure takes over. That creates a minimum, a slowest speed depth. And wherever wave speed is slowest, refraction tends to bend waves back toward it. This is the secret behind the deep sound channel. The thermocline, a cliff you can't see. Thermoclines can form seasonally and regionally. In some places the surface might be warm and mixed, then suddenly within a relatively short depth range, temperature drops hard. For submarines that matters because a thermocline can behave like a boundary. Sound from above can refract away from below. Sound from below can refract away from above. And you can create a region where sonar energy simply doesn't go. This is where the phrase, hide under the layer, comes from. But let's be precise. The thermocline isn't a wall. It's a refractive gradient. It doesn't block sound. It bends sound. And bending creates geometry. Shadow zones, when close, becomes quiet. Here's the part that feels counterintuitive. If sound rays bend downward, they can create a zone near the surface where very little sound arrives. Or if rays bend upward, they can create a zone at certain depths where sound is weak. These regions are often called shadow zones. You can be relatively close to a source and still be hard to detect because the energy is literally curving away from you. This is why sonar performance is not a simple circle around a ship. It's a shape, a living shape, that changes with temperature, season, currents, and even time of day. So when someone says, "Why didn't they hear it?" the answer might not be incompetence or bad equipment. It might be, the ocean didn't deliver the sound. The deep sound channel, the ocean's invisible highway. Now we reach the main phenomenon. Because sound speed decreases with cooling, then increases with pressure, there is often a depth where sound speed is at a minimum. In many ocean conditions, that minimum creates a channel. Sound rays that drift upward enter faster water and refract downward. Sound rays that drift downward enter faster water and refract upward. So the sound gets trapped, not by walls, but by refraction. That channel is sometimes associated with the SOFAR effect, sound fixing and ranging, historically used to locate events or signals over long distances. The point is not the label, the point is the mechanism. A depth band where sound can travel very far because it keeps being bent back into the channel. Think of it like a hallway, not a physical tunnel, a physics tunnel. And once you grasp that, you see why low frequencies matter so much. Low frequency plus channeling can equal extreme range. Why citizens feel this too, the hallway analogy. Let's pull this out of military context for a second. You've experienced a version of this in real life. In a hallway, a quiet sound can travel surprisingly far because reflections and geometry guide it. In an open field, the same sound dies quickly. The ocean can behave like both, depending on layering. Sometimes it's an open field. Sound spreads, fades, vanishes. Sometimes it's a hallway. Sound rides a corridor. And that's why sound travels far in water is not the full story. The full story is, sound travels far in water if the ocean lets it. Tactics without drama words, how depth becomes strategy. This physics creates two powerful strategic effects. 1. Depth can reduce your acoustic exposure. A submarine can position relative to a thermocline to reduce how much of its noise is delivered to certain sensors. If your noise is bent away from the enemy's listening layer, you effectively shrink your detectable footprint. 2. Depth can improve what you hear. If you place sensors where sound from distant sources is guided, you may hear things that would otherwise be out of reach. So it's not just hiding, it's also listening. This is why submarines and ASW systems care obsessively about the environment. Not politically, physically. They use profiles of temperature and salinity and compute expected refraction. Because the ocean is a lens, and you can't fight a lens by pretending it's air. Beamforming, when math becomes hearing. Now we add the third term, beamforming. Passive sonar is often about tiny differences, a faint hum buried inside ocean noise. Beamforming helps by combining many hydrophones spread across distance. If a sound arrives from one direction, it hits sensors at slightly different times. Beamforming aligns those delays, stacks the signal, and suppresses other directions. In simple terms, one microphone hears noise. Many microphones, used correctly, hear direction. This is how long arrays become so valuable, not because they create miracles, but because they give the math enough geometry to work. In the layered ocean, that directionality matters even more, because when sound is refracted, it doesn't come from where you think it should. It comes from where the ocean bent it. Beamforming helps sort that out. However, the quiet bill, why high frequency doesn't solve everything. A common misunderstanding is, if high frequency gives better detail, just use high frequency. But the numbers kill that idea. If absorption is roughly approximately 1 decibel per kilometer at 10 kilohertz, then at long distances you lose tens of decibels quickly. And that's on top of spreading loss. High frequency can be superb for short-range resolution, but it's punished hard by the ocean over distance. Low frequency is blunt, but it survives. So the ocean pushes you into trade-offs. Range versus resolution. Stealth versus speed. The environment versus your equipment. And the environment is not negotiable. Summary: the ocean decides what is visible. Let's lock the episode down with one core takeaway. The ocean is not a simple medium. It is layered, and those layers bend sound. So detection is not just technology, it is physics plus timing. Thermoclines can hide you by bending sound away. Shadow zones can make close sound far. The deep sound channel can carry low-frequency sound far beyond intuition. And beamforming is how arrays turn that messy reality into usable information. If you understand this, you stop asking, why didn't they see it? You start asking the correct question. What did the ocean allow them to hear? Closing and next episode tease. In the next episode, we'll go one step deeper into the practical side. If the ocean is noisy, ships, waves, biology, machinery, how do you isolate a target from that chaos? We'll break down signal-to-noise, classification, and the difference between hearing something and knowing what it is. Because in the deep ocean, the hardest part isn't detection, it's certainty. And that's where the real patience of underwater sensing begins.